Hello, everyone, and welcome. We will give 1 minute to everybody to join, and then we will officially start. Perfect. I guess we can start now. So, hello again to everybody who is joining us today. My name is Priya Ruzro. I'm a research associate at Mayo Clinic AI Laboratory at Mayo Clinic, Rochester, Minnesota, and I'm very happy to be with you today. Our today's webinar is Generative AI, a new frontier to medical imaging research. At the very beginning, I would like to thank SIIM Machine Learning Education Subcommittee for organizing this very exciting meeting, and I hope that we all can learn a lot from that. Before we go through the main content of the webinar, there are a couple of housekeeping stuff that I need to mention. First and foremost, SIIM members are eligible to receive one hour of ABI or SIIM certification or recertification credit. The only two conditions that you need to meet is that first, you need to be SIIM member, and second, you need to take part in at least 45 minutes of our today's talk. So if you have any questions or any concerns about that, please email to info@siim.org so you could receive your answer. And the second thing is that as we go through the different talks that we have organized for today, feel free to ask your questions and put them in the Q&A box in the Zoom menu. I will make sure to have an eye on the question box, and if anything pops up, I will take note of that. So, probably by the end of all three talks, we will have time for all the Q&As. I will try to mix and match your questions and make sure that we have time to get through all of them, but please feel free to share your questions and I will be watching them. And the most important thing, I'm very happy and delighted to be with a couple of awesome mentors and colleagues here. Dr. Akshay Chaudhuri, Assistant Professor of Radiology from Stanford University, Dr. Judy Gishoya, Assistant Professor of Radiology from Emory University, and my dearest friend and colleague, Dr. Bardia Khosravi, a research fellow in our lab from Mayo Clinic. And we are going to hear a lot of very exciting talks, I'm pretty much sure, from each of these people. But before that, I'm going to give you a very, very brief introduction to the chat that we are going to have today. Now, let me start by telling you a very funny experience that I had a couple of days ago when I was introducing generative AI to one of my friends who is not that much tech savvy. And, he asked me what this generative AI is. And I tried to, explain with all the fancy technical stuff that we usually do and we usually say to other people. But at the end, the take-home message that the person had was that, in my eyes, in my mind, generative AI is basically something that you use when you want to go through a very long email and summarize that into one bullet point, or vice versa, if you have something very short and you want to write a very long email about that and say, hey, I've been thinking about that for so long. So that's unfortunately a very specific day that some people might think about generative AI, and specifically after the emergence of these new large language models, ChatGPT, GPT-4, and other models. People are a little bit more tended and inclined to think like that. But, and this but is very important, we have many other people from the scientific community who are thinking about generative AI in a totally different way. I have put some of the recent research papers or, tweets or news that I found about generative AI. This is, and if you're on Twitter and if you're following the hashtag generative AI, you all probably have seen this before, but, just to show you a couple of examples, very awesome models and very awesome tools came out. The MedFlamingo tool is actually a multimodal medical generative AI that can understand images and text at the same time. And, Monai recently released the package Monai Generative that actually can use diffusion models, those fancy new generative AI models that Bardia will talk about to generate images. And then, there is this fancy competition about which generative AI model is going to be the other, even in the field of medicine, as you can see on the right-hand side article. And this one, which is quite interesting, I really wanted to put the entire image from the paper here for you. So the LLMs, which is actually, again, training a large language and vision assistant for biomedicine in one day. And if you can see, if you look at the capabilities of this model, it receives a caption, and then it gives you a chance to have a conversation with AI regarding a text and an image that is corresponding to that text. So it's not like that everybody, specifically in the scientific community, is just looking at the surface of generative AI. There are a lot of people who are thinking deep about generative AI. And hopefully today we will also learn how to do that and what specific milestones people have reached in the world of generative AI. Now, if you are into AI in general, you might also have heard about some of the hypes or some of the big predictions that some people, even some famous people as famous as Geoffrey Hinton, has made about AI. So if you remember, if you are a radiologist, you probably have heard this before. Geoffrey Hinton years ago made this prediction that radiologists look like to be as the coyote already over the edge of a cliff. So his recommendation to programs was to stop training radiologists. And very interestingly, a couple of months ago, he was asked, because he, on that time, made a prediction that in 5 years, there is not going to be any radiology training in the world. And 5 years passed, radiologists were still there. So somebody went to Hinton again and asked, hey, what was wrong with your prediction? And he simply said that, no, I was just wrong about the time. Probably I needed 10 years instead of 5. So there are a group of people, even very talented, very educated, scientific people like Geoffrey Hinton who think like that. And also there are a group of other scientists in the world of medicine or even beyond that world that think that no, AI is still there. AI is a tool. We can use that. And if we know how to use that in a safe and equitable manner, it's going to add a lot of values to our workflow in the medicine. So there are two different standpoints, way of thinking about generative AI. And today, we are going to see how our speakers think about that. And even if you have anything on that, please feel free to share it in the Q&A or in the comment box in the Zoom so that we could also hear about it. Now, I'm going to stop talking here. There are only 2 polls that I would like you to take part in those. I'm going to launch the first poll for you here, which is about somehow related to the very famous quote of Dr. Hinton, asking you, will generative AI or AI in general will put any medical specialty near the edge of the cliff? So feel free to answer, very honestly. These polls are anonymous, yes, no, or I don't know. So I'm going to launch the first poll for you. And I will give you about 15 seconds or so to answer that. And hopefully our speakers could rely on these answers to maybe adjust, fine-tune the content of their speech a little bit in the last minute. Perfect. So this is quite interesting. I honestly thought that a lot of people would say no, but the answers is kind of shocking. Okay, it's very cool. It's very cool. Thank you. I will give it 5 more seconds and then move to the next poll. Perfect. So 32% yes, 42% no, and 26% I don't know. I guess that's a cool start. Now let's go. I guess I can share the result to you. All right. Not sure if you're seeing that or not, but perfect. Okay. Now let me go to the next poll and ask you something else. Now here, I'm going to ask you about what should be the most important priority of generative AI researchers in medicine. Now, there are a couple of items here, sharing and presenting more real data for AI training, because we all know AI needs data. Second, using AI to generate more and better synthetic data. Third, training larger, more sophisticated or multimodal AI models. Fourth, demonstrating the clinical applications of AI models. Fifth, identifying and mitigating bias. Seventh, addressing deployment gaps. And finally, developing policy and regulatory framework. So while I'm launching this new poll, the only thing that I would like to mention here is that probably in many of your minds, you think that there are more than one item here that you should choose. And I do acknowledge that. But our goal here was to only seek that burning need that you feel and you realize that we should attend to more than the other items that you see on the screen. So feel free to choose one of them. And again, I'm going to give you 20 seconds for this because I know it's a little bit longer, but hopefully very soon we are going to start with the talks. All right, so again, quite balanced results here. All right, so again, my prediction was wrong. I personally thought that probably addressing deployment gaps might receive a better attention from the attendees here, but that's currently the least favorite one. But almost all other options are quite balanced. So I will give 5 or 6 more seconds and then share the results with you too. Perfect. So feel free to take a look at these results too. I guess the winner is actually developing quality and regulatory frameworks, which might somehow address the previous poll item too. And after that, we have demonstrating the clinical applications of AI. And the least favorite one, as I mentioned, is deployment gap. So hope this sets the scenes for our distinguished speakers. And with that, and without any further ado, I would like to invite my friend, Dr. Bardia Khosravi, to start his talk and go through the first presentation. Again, feel free to put your questions in the Q&A box. Bardia,
Thank you
please.
so much, Puriya.
Yep.
So let me just share. Okay, can you see my screen now? Great, thank you so much. Thanks Puriya for the great introduction. And without further ado, let's start. So what is generative AI? Generative AI is, let's say, creating new types of data or new data based on a distribution that the model was trained on. So let's say ChatGPT, I think everyone here have used that, or almost everyone. And that model was trained on texts that are present on the internet. But it can generate texts that look like those data, but very similar to those data, but you might not find the exact match out there. So it's more than just a retrieval system. You don't just search the internet to find some results. You create some new answers. And that's the scary part, at least for language models, that this looks too real and it might be very deceiving. Today, we're going to talk about medical imaging or imaging in general. And we'll focus on, please, in my talk, I'll be focusing on 3 approaches. One, variational autoencoders. They were introduced back in 2013 as a way to create images. And first of all, they were proposed to create somehow a compression algorithm, as we'll discuss. The second one is generative adversarial networks, and it was introduced back in 2015. You probably have seen the results of this type of networks. If you go to the website, This Person Does Not Exist, you see a lot of faces that were created using this technology. And lastly, diffusion models, which really took off at 2020. They were introduced back in 2015, but they took off at 2020, and they are currently the state-of-the-art generative model, or the backbone of the current state-of-the-art generative models. I'm going to give a brief technical overview of these models and compare them, and then give the floor to Akshay. So, variational autoencoders. As we said, these models will have an input. They have 2 components, an encoder and a decoder. The encoder is responsible for compressing the information into a space called latent representation. So this image, let's say it's 512 by 512 pixels, which is a lot. And then the latent representation can be 1/5, 1/10, 1/30th of the original image. So it's compressing that information. And then you train a decoder to bring back this latent representation to an original image or an output that's very similar to the input. So this is a compression algorithm. And by doing this, there is a chance that you might lose some information, which we'll discuss later. That's why these 2 images are not completely similar. Next, generative adversarial networks, which I personally really like because the idea behind them is very fascinating. So we start with a latent representation, which is just, here we call it the same, but it's just a set of random numbers. You feed it to a model, which is called the generator, and it will give you an image, but it's fake. By fake, I mean it's generated by a model. Then you feed this fake image to a discriminator or a critic, and also you'll give it some set of real images. And you say, okay, the job of this discriminator is to say which one is real and which one is fake. So the generator, which we will use for image generation at later stages, will not see the real images. It's only relying on the feedback from this second model to be trained. Then we have diffusion models. So diffusion models work in two stages. First, you have an initial image. You gradually add noise to that. You make it noisy, noisy, and noisier until you end up with pure noise. And this is called forward diffusion. It's just math-based. You're not doing any sort of deep learning thing or machine learning stuff here. You're just adding noise based on a schedule, which you already know, and then you end up with pure noise. Then your diffusion model also has a backward or reverse diffusion, which is using a deep learning model to denoise this noise. And then when the model is fully trained, you can give it some random noise and then come up with a clear image. So this is how diffusion models work. There are many diffusion models out there trained on natural images. The two most famous ones are DALL-E 2 and Stable Diffusion, which the second version of that, sorry, the X-large version of that was released recently. These models are very good at being conditioned. So you can condition them on a text. Suppose that we have an astronaut riding a horse in photorealistic style, and it will give you this image. It doesn't exist, but the model at least knows some concepts about what the horses look like, what astronauts look like, what's their suit like, and yeah, a horse can be jumping or whatever. So these are the concepts that the model has learned, or it's pretending to learn. And this image was created by the DALL-E 2 model. But these models are not very good at, their training data is not rich on medical data. As an example, if you ask Stable Diffusion to create an anterior-posterior pelvis radiograph of a female in their 60s with an implant on the right side, so no pathology, it's just simple stuff. Things that you will see later are more fascinating. But here, you'll see it will give you this. It's beautiful, it's aesthetically very good, but that's just it. It's just aesthetically good. It doesn't look real, it's not plausible, or it cannot be used for anything downstream. It's good for art. So, having said this, what's the best image generation algorithm? So for a model to be good at generating images, it should create high quality samples, it should be fast, and it should have it should create diverse set of images. The algorithms that we discussed, each of them will have two of these. So variational autoencoders are fast, they're diverse, but as we're doing some compression and decompression, we lose some information. So these models might cause some might create some low quality images. Then we have generative adversarial networks, which are high quality, they're very fast, but they suffer from a phenomenon called mode collapse. It means that if you're trying to generate 10 numbers, the model will learn to generate 5 of them very good and will forget about the other 5. So that's called mode collapse. It reduces diversity. And then finally, diffusion models, they create high quality images. They're very diverse, but as you saw, we're going to denoise step by step. So the sampling rate is slow. This is called the generative image generation trilemma. Oh, I don't know why are these hidden. So all of these models on their own lack one of these 3 components. And one way to address this is to combine them, which I think Akshay will going to talk about. And with that, I want to thank Purya, my dear friend, who without this, it wouldn't have been possible to explore any of these ideas. So he's my partner in crime, so we do everything together. And thank you so much. With that, I'll give the floor to Akshay.
Thank you very much, Bardi and Purya, and thank you very much for SIIM for inviting me to talk about some of my work. Let me go ahead and share my screen real quick, and hopefully everyone can see the slides okay. I'm not hearing any indication. So, okay, perfect. This was a fantastic introduction about what sort of tools one can potentially use that rely on some of these generative AI tools. But right now, like it was shown in the previous presentation, most of these aren't really focusing on medical imaging domains. So how do we take some of these very powerful tools and make them useful for us? So hopefully over the next 15 minutes or so, I can give you a high-level overview of some of these. And this will specifically be focusing on how can we actually use these tools for images. So compared to things like ChatGPT and GPT-4, these are text generative models. So the input is text and the output is also text. Here, the focus will be on outputting images that could potentially be useful in medical imaging. So I think, like this was covered in the previous slide, some of these text to image foundation models can be very powerful. So we can enter in different prompts, such as a photo of a corgi wearing a hat in Times Square. And using some of our latest and greatest models, we can generate images that have high semantic quality as well as high resolution. This image probably never existed. I can most likely guarantee that this image of a oil painting of a raccoon queen has never existed. Yet we can actually really learn expressive features from this text prompt and convert our language embeddings into pixel images that can actually be semantically plausible. And we're mostly just limited by our own creativity into what sort of images we can generate. But again, like it was shown in the previous presentation, if we prompt these models with any medical concept, so here we're trying to focus on chest radiographs, these images look cartoon-like. These are not useful. These don't necessarily represent what we care about in medical imaging. So we wanted to ask, well, if we have the ability to represent some of these medical imaging contexts, can we actually do that? Can we leverage these large models that have been trained on billions of image and text pairs and make it useful for radiology? And I think there's a lot of potential for generating some of these synthetic images. But even before we do that, we really wanted to consider, why would we even want to generate some synthetic medical images? And I think there's a few reasons. And I think the first and the simplest reason is potentially we can use these synthetic images in lieu of real images. For most medical imaging machine learning applications, we're always in a data scarce regime. So if we have the ability to train better models using some synthetic data, maybe that can improve the performance of our downstream classifiers or downstream segmentation models. Right now, another problem is class imbalance and a lot of the abnormalities that we're trying to evaluate. We typically have a long tail of distributions that we really want to be able to get correct for our classification tasks, but we just don't have the data sets to be able to do that. So potentially synthetic data offers hope for that. And I know Judy will be touching on this a lot more, but right now, I think there's a big emphasis in trying to make sure that all these models that we're building, generative or discriminative, we really want to make sure that they work well across all sets of populations. So that's currently not the case. There's definitely different subgroups within our data sets that have unequal performance. So maybe using synthetic data, we can patch for these performance gaps. So I think all of this could potentially be beneficial for synthetic data generation. Another aspect could be privacy preserving machine learning. It's challenging to be able to aggregate multi-site data. So here, if we have 3 different hospitals, we might currently build 3 different models. I think there's a lot of active research going on in things like federated learning to be able to pool data sets from multiple different sites. But I think synthetic data generation provides a new paradigm for being able to preserve privacy. If each site generates their own generative model, they can pool together all these synthetic images. There's no PHI that's contained in them. So potentially we can just train larger models using information from all these multiple sites. And I think lastly, another opportunity is if we can generate synthetic images, potentially we can use this for medical education. Instead of waiting for case files to come along showing the exact cases we want to be able to teach with, maybe we can just prompt the model to show different abnormalities, to show different pathologies, and we can do this in a very systematic and standardized manner. So I think this area has been explored a little bit less, but I think it's a very exciting area, not just for research, but really being able to train the next generation of radiologists. So basically, what we want to do is we want to take some large-scale models, such as stable diffusion in this case, where if we prompt a model and this is the current performance, how do we take this large pre-trained model and generate images that look something like this? So this was really work done in our group, which was led by 2 really bright students, Chris Blutkin, who's a thoracic radiologist, and Pierre Chambon, who's a master's student, that were able to take this large-scale stable diffusion model and we're able to adapt it to generate very high quality chest radiographs. And we call this model Redken. Interestingly, we came up with this name using ChatGPT, so you can't really get away from that. But you can really see some of the expressive capabilities that models like this can have. So if we just start off with some of these images on the bottom, we can ask the model to generate an image of a big right-sided pleural effusion, and we can see exactly that particular finding. It understands laterality, so it knows the difference between right-sided, bilateral, and then left-sided pleural effusions. It knows the difference between big and small. So there's a lot of expressive capabilities that this model has that can really be tuned and guided using text instructions. And this has never been possible using methods like GANs that are always conditioned on specific classes. And you can't really provide these fine-grained semantic features into a generative model. So I think this is a very exciting opportunity. And over the next few slides, I'll briefly talk about how we trained this model and some interesting application areas that it can enable. So we learned a little bit about how some of these diffusion models work, and this is the underlying architecture of the stable diffusion model. It's very complicated if you just look at this slide, but we can actually break this down into three very simple components. The first component is a variational autoencoder, and we just learned a really nice lesson of what a variational autoencoder is. It takes a very high dimensional image, and then it compresses it into some low dimensional representation. That's all that we're trying to do. Instead of working with high resolution images, we just work with more compact representations. So that was the first part of the stable diffusion model. The second part of the stable diffusion model is exactly that diffusion process that was described in the prior presentation, where we iteratively learn to denoise images. So we start off with a real image, and then we add a little bit more noise, and we're just learning denoising in a very local step-by-step manner. And then this provides us the ability to generate unconditional images. So if we start off with noise, we'll generate some image, but we don't really know what the output would be. So that's where the third part comes in, where we can take additional priors and we can actually guide what the generation of this model looks like. So this guidance or this conditioning mechanisms can exist in various different forms. We can have text, which we've seen a lot in this presentation already. We can have different images that we can condition on. So generate a chest X-ray that looks like this other chest X-ray with some additional findings. So there's a lot of customization that we can actually build into these models. And I think one of the benefits of these diffusion models is that you can really combine multiple different conditioning factors all at once. So we can have semantic maps, and this could look like, a simple segmentation map of lungs, of the heart. We can have text, we can have images. So it just provides the end user with a lot of flexibility and control about what they want to generate downstream. And now that we have a model that has the potential to generate this, we really wanted to evaluate how well does it work. It's really hard to do these evaluations because there's no very good image quality metrics. So we tried to define three holistic philosophies to understand, is your model actually working well? So the first philosophy that we had was, can this model generate high fidelity images? And this term fidelity basically describes that your synthetic data should look like real data. I think that's the first minimum threshold that we need to be able to pass. And based on some of our early generative results, we're able to accomplish this quite well. That we could probably have a radiologist distinguish that this is a real image and this is a fake image, but that's not really the goal. Based on some of the conversations we had with thoracic radiologists, there's this notion of a visual Turing test, where a model is good. If a radiologist can't tell it apart, I would maybe rethink that philosophy. A radiologist could potentially still tell things apart, but that doesn't make the model any less useful based on what we're using for a downstream task. We observed that with our generative images, it would take a radiologist around 10 or 12 seconds to accurately figure out whether or not an image is synthetic or not. But they really had to look. They had to zoom in, they had to change the window level. So I think the generative capabilities are increasing, but necessarily fooling radiologists, I don't think that's the best metric we should strive towards. So the second aspect that we really wanted to optimize was we wanted to cover a diverse set of our training data distribution. Instead of just being able to generate one abnormality or one specific pathology, we really want to be able to generate the whole slew of findings that we might see in a day-to-day clinical practice. So we really want to be able to generate the entire data distribution rather than specifically focusing on one or two modes in our data distribution. And then I think the last tenet that we wanted to evaluate was, are these samples authentic? Which basically means that we simply don't want to copy training data and just perturb the image a little bit, just rotate your lungs slightly, just shear them. So these are the three guidelines that we really use to evaluate our model. And no evaluation is perfect. I think we're generating images and then we're trying to come up with better criteria to evaluate them. But at least this is how we're thinking about the qualities of generative models. So if we look first at this notion of fidelity, can our models generate synthetic, real-looking images? Here is a column of 2 real X-rays. Here's if we just take the original stable diffusion model off the shelf. Here's an approach that we tried initially where you could actually fine-tune the stable diffusion model with a few hundred radiographs. So you can definitely see that the quality is systematically better than the original stable diffusion, but it still looks very cartoonish. It doesn't necessarily have the right high resolution texture, the features, the noise. So if we actually continue fine-tuning this model and we generate our model called Redken, we can see that the realism is starkly better. And at first glance, one might say that the models that are generated from Redken look pretty similar to some of the real images that we might anticipate. So we're pretty excited about this finding just in terms of plain image quality. Next, we really wanted to see what sort of findings can this model represent. So we just prompted this model with different imaging findings that one might expect to see in clinical practice. So here's 12 different images. I won't necessarily go through it one by one, but we were able to see that this model actually learns to generate all these common findings one typically might see in our day-to-day practice, and we have all these models that are annotated to actually see whether the model is right for the right reasons. And this model only learned in a completely unsupervised manner. There's no human annotation that was required. We simply fine-tuned the model on the generated on real images as well as the corresponding radiology reports. And just by doing that self-supervised pre-training, it can really understand some of these interesting concepts that pop up from time to time. So it's really exciting to see that we can generate these diverse outputs. And lastly, if we prompt the model with the same prompt multiple different times, if we go back to our slides about stable diffusion, we always start off with some random noise. But what we can do is we can keep our prompt the same. And if we generate different random noise to begin with, we'll start seeing slightly different images that are outputted. So we can really span a wider data distribution with exactly the same input. And I think you can think about this as a feature and not a bug. But with a diffusion model, there's an inherent stochasticity in the generative process. Here, we're leveraging that stochasticity to generate something useful. So this is all great. We can generate models that look nice, that make us happy. We can pat ourselves on the back. But we next wanted to see, what is it actually useful for? Can this be more than a simple toy that looks nice and creates high quality images? So we just ran a very simple experiment where we tried to train a downstream classification model using some of these synthetic images. So here we're seeing 3 specific curves where we're training a chest X-ray classifier on a whole host of different abnormalities, and this is using the MIMIC dataset. So on the x-axis, we see how many training images we use. On the y-axis, we see the performance of our model. And then there's 3 types of models we train. One using only real data, one using synthetic data, and one using a mixture of both. And right off the bat, we'll see that our models aren't as good as training on real data, but they're actually somewhat non-inferior. If you see this green curve, it just lags behind the real quality images. So only training on real images is almost as good as training on synthetic images is almost as good as training on real images. And note that all the evaluation here is done on real images only. So that was a good first sign. But what was even more exciting was if we take the same model and then we transfer it to a different data set. So this is a Checkspert data set. We know that most machine learning medical imaging models have issues with generalizability. When you train on one site, they don't necessarily transfer to other sites. But when we did this transfer, we noticed that the model that was trained on synthetic and mixed images always performed better than the model trained on real images better. So in this case, synthetic data improved generalizability and it had better out of distribution robustness. We saw similar findings on a different data set too. So I think these are all very preliminary experiments. We can get a lot more complicated in trying to generate specific images. We can do things like prompt engineering, which is very popular in NLP. But this at least gave us some credence saying that these images could potentially be useful. And because we think these images could be useful, we want to be able to share this model broadly with anyone that wants access to it. Here's a QR code. As long as you have credentials to be able to use the Mimic dataset, we're more than happy to share these models. Training these models took a fair amount of compute. The final model took around 2,000 GPU hours. So we want to be able to make sure that we can share the model with as many people so we don't have to replicate that training again. So please go on the QR code and you can get a link to where you can access some of these weights. So overall, as I conclude this talk, I think synthetic data that we can generate using these text-to-image models can potentially cover some of the challenges that we have about small training data sets for medical imaging. I think there's still a lot more work to be done, but at least this provides us with another avenue that we can use to build better downstream models. And I think this opportunity exists for arbitrary downstream models. This could work for classification models, segmentation, detection models. So I think there's a lot of potential here to continue exploring in this space. And at a high level, all of this is really enabled by having a large scale of paired data. We have paired images as well as the corresponding radiology reports. And if we can learn in a self-supervised manner using these two paired modalities, that's all it takes to be able to generate these high quality images. So I expect a lot more work to come in this space. But for now, thank you very much for your time and happy to answer any questions towards the tail end of this presentation. Thank you all.
Thank you very much, Akshay, and also Bardia. Judy, if you're prepared, we can continue with you.
Thanks for the invitation to present today. So I'll just speak about generative AI and implications of bias. And what I have to say is that, the excitement around generative AI, and especially, following up with the prior speakers, number one is, as radiologists, we always live multimodal. This interaction of text and images is not new to us. And, we see this opportunity as this natural way of thinking about how we understand text and how we use medical imaging, as not even sort of like the general AI, as some people may see this potential for the foundation models, but as sort of like a fundamental way of building AI that works. And so from the previous speakers, you've heard that most people are saying we're learning what are good imaging metrics. We're learning, and so you can imagine if you're just learning about how to do performance, what are we going to do when it comes to thinking about bias? I feel that we're just barely scratching for the general, even AI applications and data science. Here are my disclosures. And so, was presented initially. I mean, you cannot make a talk today without showing Geoff Hinton, but more especially, I wanted to show this and sort of this huge concern and this anthropomization, especially when we sort of the general public sometimes lives in this multiple dimensions, almost thinking like imaging is separate, text is separate, audio is separate, and instead of sort of like this opportunity that is amalgamated. When I try to explain still the most simple way of the large language models, I like to think about them still as if you could access all of the world's text and you were able to understand and transform it to new words, for example, Judy Badia or Judy Anna, Judy, someone else, and you started to understand the representations, then you would get a foundation. And from that foundation, you can come back and now build tasks. For example, when we think about the large language models that have been used for, to power chatbots like ChatGPT. And so if we were to think the same way for MedPalm, which is the model from Google, and they use the USMLE benchmarking, so you'd be starting off with a foundation, but then you'd have to come back with what's your task. How are you going to evaluate your task? And so the first area is, how do we determine task? And I'll show you a practical example of how we've done something like this. And this is really an area of requiring a lot of work, and still an area where you can capture just the sentiments that are the average. And so if, and so requiring a lot of human feedback to try and keep the AI safe. But since perception, maybe my perception of terms is maybe different from Akshay, then that can build a slippery slope. And that's when you hear, well, MedPalm is being used in low resource countries in Africa, then you really wonder, how can that be when MedPalm human reinforcement feedback was done from clinicians in the US, UK, and India? And so this area of human feedback is an evolving area. Most people will know it as the red teaming activities. And some of the principles are, thinking about low likelihood of medical harm, alignment to general scientific consensus, precision, and lack of bias. And as this sort of evolves, then what we've seen is that even the output of the large language models has started to evolve, creating, if your application was using a different version or you are asking the same information differently, then the result is changes. And so then there are these sort of controversial questions, sort of like this society questions where there's no real answer, and so trying to test the models. But the big thing again here in terms of seeing sort of harms or even an improvement, or the other flip side, an improvement in the equity perspective, then it's difficult, because how are we going to tame this, these models when we cannot even get a baseline for their performance alone? And so if we look at some of the examples, these are the X-ray GPT, and this actually came from Mujin, and most of this is around performance, right? So you can see that here it says, well, there's left diffusion, the test tube is seen on the right side, not displaced, and you kind of see sort of some of the pitfalls. And the reason why I show this example is that quite a lot of these generative models, not because of their function, which clearly needs some more work, but on the other hand, can be really troublesome when it gives you confidence that you may not need the subject matter experts. And so I feel that even for myself, which was some work I've been doing with Badia, is interesting to try to think, how do you benchmark, or how do you even get a similar performance of a model that is based on, even in the real world setting, to understand when this fails. Here's an example, not in radiology, trying to say, hey, what are the responses? Are they good? And they did come up with the questions themselves, but you can imagine if we had to do something like that in radiology, that would be nearly impossible. And then this other thing, sort of soft skills around that they felt that, this like the bots, the ChatGPT generated responses are more empathetic, right? So it's now no longer that the physicians needs to work with AI, but that the agency alone of the bots themselves can be very reassuring. And if you look at some of these responses, this was a question about risk of dying following swallowing and ingesting a toothpick. You find the chatbot response is more wordy and the physician response is accurate. But this one of the pitfalls, what I'm trying to show here, is that it's not really that still the average representation of text, that there's so much manipulation when it comes to how the information is represented to you. And so this believability means that even when the model is wrong, is incorrect, you feel that you still want to align to, there's a little bit of manipulation, and that makes it even more difficult to understand the performance, because it's not just the raw output of the data. One great example I like to give here is to say, if you were to just plainly say, GPT, write me an essay of 3,000 of an essay about Kenya, then the next predictions, because most of those appear in assignments, it would really just say, make it 3,000 words and blah, blah, blah. But because of the human feedback and there's no real transparency around how that is done, then it's, it lands that, well, when Judy says that, or most people say that, they're not really trying to get additional instructions, they're trying to have you generate the essay. And so, and then we have this evolving regulation, and we see some of the crazy things, for example, firing all your mental health experts or your obesity experts and, replacing them with chatbots. And it's this area that is changing in terms of how we regulate how these large language models are used. It turns out that when you have a patient-physician relationship, then you can sue, you can get sued or you can sue someone. But when you have patient-facing AI or direct-to-consumer health advice giving, and I want to remind you that some of these technologies are very accessible to the general public, and you just have to copy your healthcare information, and using through the success of the Cures Act, this is actually very possible. And so this sort of looseness and sort of some of this decision making, I think, creates a big risk for their application. Now, we have done some of this work where we show that ChatGPT can simplify radiology reports. And what is interesting is sort of like some of these human values or human perceptions that are embedded in the prediction. So for example, you could say, simplify this report, make it to someone appropriate to someone who lives in a specific part of the world, or with concerns. So it's trying to generalize some sentiment, and I think it's going to be interesting because that may be readable and more understandable, but I don't know sometimes when we cross the bias and have moved a little too much. The reason I showed this work is that this is an example that was done by an ear doc who was trying to see how can you use, for example, ChatGPT to diagnose patients, put in 40 of their cases, and they saw like some of the worst performance was for a 21-year-old female with right lower quadrant pain, where there was no ectopic pregnancy. And what it worked well for, not surprisingly, was classic presentation. And so the perceptions, or wherever the data or wherever sentiment or averaging that we get, is really what is going to be moved forward. And I hope I don't have to really emphasize on the challenge of systemic racism and how that still average treatment is what can get perpetuated. And so we see quite a lot of these technologies getting into the as an intermediary, with the recording. I think you've seen some of the videos that are coming here, but we know that minority patients tend to even modify their behaviors when they're in the doctor, dress differently, speak differently, so that they can at least be heard. And so it's going to be pretty interesting, not necessarily in a good way, but it's going to be an area of interest to even see how some of these changes evolve and mediate the physician. Now, when it comes to medical imaging, we do know that the AI models have been shown to demonstrate very great ability for predicting demographic information. And we took something similar actually from Chexpert, and what we found is that actually, some of this, and this was not a lot of conditioning, but some of the hidden signals, and this is why I'm showing this, where we see that the models can learn things like race. I think we can understand some of the implications and downstream tasks, and so you make data sets that can even improve the explainability of some of the AI systems that we're using. And what I have to put in as a word of caution is that some of the patterns that we observe are barely understandable to us when we create the data sets. And I believe as we move to synthetic data, that is still challenging. So I'm going to end by showing you this work. It's still under peer review. When we looked at, well, I already said it's really difficult. The scope is so big, even just to understand performance, let alone bias. And not that those two should be studied differently. And then the second thing is, even how do you get started? And, this work for me, because as someone who works in this space, is an opportunity to reflect about my work and how to even evaluate some of this model. And what we did was we looked at 3 evaluation areas. How do you simulate patients for medical education? How do you construct differential diagnosis? And how you assess subjective features? And so medical simulation, you just give, compose a brief presentation of a patient presenting with maybe diarrhea, and then provide demographic information and medical history. And then differential diagnosis, you would give this. I remember this really should be ranked. And then it would also give you like the next step. And we use this case collection from the New England Journal of Medicine. And then you can see some of the differential, sort of like the differential diagnosis. And you can see, for example, the true incidence is the diamond red. But when you you can see sort of like the GPT estimated. So for example, sarcoidosis tends to be seen more in, is postulated that it's seen more in Black females, and so some of the general perceptions, as we've known, it's a learning process for understanding how race has had an impact on medicine. We still see the same when we generate data sets or action items from the same public data sets. So those biases are not removed. I think even what was most surprising is, when you give, for example, a specific symptom and say generate some differential diagnosis, you can see, like, for example, if you're Black male, when for the same sort of symptoms, you can see that you're most likely to have HIV or syphilis. And so some of the society biases are very, very much amplified and seen in the generative models. And also when you see sort of, should we refer the patient for additional imaging? And you see that there's a difference when for just referral, this was done using like a cardiology data set that was done for unconscious bias, or, and some subgroups of patients should not be referred more to the patients. You can see even a difference between male and female. And then there was this other subset, this was done using some nursing data set. And it's just trying to say, like sentiment learning, what do you think? Is the patient lying? Are they exaggerating? Are they pain of pain? Do you think they're abusing Percocet? Are they hiding their history? And you see differences in terms of what the agents are able to return and maybe agree. For example, like the white males here are exaggerating their pain, and so it's very different. And this is not even just the patient, you're just talking about them, just the clinical information you provide and how you interact with them. And so I think that we will the appropriate benchmarks, and there's quite a lot of work to be done with that. But as we do that, we do need to understand where the source of the data is and what biases exist in some of those data sets, and also to understand the systematic area where these technologies are going to be used. Patients can access their medical information, maybe not as easily for medical imaging, but it doesn't mean that it's stopped, that they're going to try out some of these techniques, especially because sometimes it takes a while before the doctor gets back to you, and now you have an agent who's more believable, can tell you things, and you may not really know when those things are different for you. And when it comes to medical data, we know quite a lot of the text part is quite duplicated, and we need to understand what will be some of this downstream. And then I talked about who vets the human feedback and what is important, whose opinions are really embedded in the technologies that we used. And and what sentiments as we start to amalgamate bigger data sets, but also not forgetting that some of this ability, for example, using Actions model to show me a subset of patients can really move the needle forward, especially for rare diseases or intersectional biases where patients make across different groups. So big things is just to say there's a lot of work to be done, and I hope that you're inspired to contribute to this space because it's going to require a lot more people. Thank you.
Thank you very much, Judy, and thank you everyone, all our speakers, for the fascinating talks. I really enjoyed and learned as I predicted. So thank you. And I'm going to move to the Q&A section. Let me share my screen and bring back the slide for the final part of the webinar, and then I can also ask you some questions. So first of all, I guess our speakers already answered most of the questions that were raised in the chat, but I also took note of a few interesting ones that I thought might be better to discuss at the end of the conference. I actually have one question for each of the speakers, and then if we have time afterwards, we can go through more in-depth discussions about other questions too. So first, let me start with Bardia. So Bardia, you kindly introduced the different, the very famous ones, at least, the modalities that we could use or architectures we could use for generating AI models in the domain of computer vision. Now we know that nowadays, most people talk about diffusion models and how these models are actually everywhere, stable diffusion, other kind of architectures. My question is that even though they have this, bottleneck or limitation of being a little bit slower than other models, we also know that a lot of new techniques are coming up that is somehow making up for that specific limitation. We have faster samplers and things like that. Now, I mean, in such a world, do you still see a place for those older architectures like GANs specifically, or autoencoders, although we all know that variational autoencoders are still in use in stable diffusion. But let's talk about GANs, for example. Do you still think that in the upcoming years, somebody would prefer GANs to diffusion models in any specific ways, or should we say goodbye to those models forever?
So I think it highly depends on the context that you're trying to use those images and the resources that you have. Training GANs is, in my opinion, much less resource intensive. And although the results might not be as good as, in terms of diversity, as good as the diffusion models, but if you have limited resources, training a GAN is much easier. Fitting it on your GPUs and smaller GPUs, it might be easier. The other thing that I wanted to mention is that, as you and Akshay mentioned, these models are being combined with diffusion models. So we have diffusion GANs that's also trying to just have faster sampling, but using GANs. So I think the future will be a smart combination of these models, so that we have all the three components in one single model.
Awesome, thank you very much. And now moving to Akshay. So Akshay, I guess I have kind of similar to this conversation with you once in the Twitter, but because one participant also brought the question up, I saw your answer to me, but thought it might be better to also have your opinions mentioned verbally at the end. So you, in a very interesting study, showed that the synthetic data, if added to the real data, could actually increase the performance of downstream models, or at least be as good as the real data. Now, my question is that, as Judy mentioned, we know that models, AI models, could amplify bias. And the question is, if we are moving towards a vision in which these generated images, these synthetic images, are kind of popping up everywhere and being mixed into the real data, how can we ensure that the downstream models that we might train on a corpus of real and synthetic data are still free of bias, or at least do not have a significantly larger bias compared to the models that were previously trained on real data? Is there any measure that we can take to mitigate that kind of threat?
Yeah, that's a very good.
Sorry, but that's not a technical problem, though, right? But I'm curious to hear actions.
Yeah, and I think this is a very important question we should be asking, and this is exactly something Judy and I are working on together. So we know that some of these computer vision models have the capability to discern what the age of a patient might be, what the race of a patient might be, what sex a patient might be. So we can use those for classification. So now there's definitely some features that we might not always be aware of that the models can still learn. So now can we actually just leverage that into our generation process? So instead of saying things like, generate a chest X-ray for someone with cardiomegaly, can I now prompt the model saying, generate a chest X-ray for someone with cardiomegaly who also happens to be a 45-year-old Asian woman? This is something we're actively working on because this metadata is always available either in the patient's medical record or in the DICOM metadata. So now, in addition to conditioning just on a text embedding, we also have these class conditional embeddings that we can condition on. And will it be perfect? No. I think there's a question that Joe asked in the chat. Will we solve the problem of bias? Not at all. But at least if we can mitigate that problem a little bit with these approaches, we can combine a lot of different methods to eventually get to a state where maybe we'll say that maybe bias isn't a problem, but will we be there with synthetic data generation? No, but I think there's a lot of potential these models can have. But curious to hear what Judy has to say about that too.
Yeah. So I also think there's a role for just understanding the process, right? So we're seeing quite a lot of consortiums like standing together, coming up to say, let's improve how we talk about data sets, right? So Akshay lives in not in a data desert, right? He works a lot to release data sets, not just the synthetic data. But if you think about how some of even these data sets are going to be merged with the downstream users, there may be no transparency and data set documentation, and we may not even understand what exactly should I be documenting, right? So for a long time, we've been curating. It's the same thing I started by saying, you live in these two worlds where you treat text differently and imaging differently instead of treating them together. And so if you even look at some of the earlier data sets, if some of our work would never have been able to do with public data sets because they didn't have that type of rich clinical metadata. And so I think in addition to what Akshay is saying is that there's needs for process and even understanding what will be the significance of some of the data set standards that are going to come out and say, hey, this is, for example, you need to know that this is going to be different. There's also something else that is being increasingly used is these embeddings, right? So this impact of what I call a new data sets, right? We saw the work from Google looking at chest X-ray embedding. So you have this plethora of original images, embeddings, and synthetic data, in different forms. And we really don't know what the downstream impact of those data sets are for real world use, in my opinion.
Awesome. Thank you both. I mean, there are a lot of things that we don't know, but there's still a lot of exciting things to research on. We are pretty close to the end of the session, but I would like to ask one final question from you, Judy, too. Sorry if it needs a long discussion. I try to, raise the question fast. So, you mentioned a lot of the threats that relying on these generative, or better to say, careless relying on these generative AI models might have in terms of bias. Now, let me ask you the other way around. I mean, is there any way, or is there any, at least direction in research that we could leverage generative AI models themselves to mitigate bias, maybe in the generations of some other models, or maybe in some other AI domain? Judy, I'm not seeing your image, but if you're talking, you're on mute.
Sorry, I had a little bit of a breakup. Could you repeat the question?
Yeah, sure. So the question was, you talked a lot about how generative AI outputs could be actually biased, or at least we should be careful about how to use them. The question is, can we also rely on generative AI models to address or mitigate some of the biases that might be generated by other AI models?
I think so, but I still think the big takeaway from this presentation today is that we are in the learning process, right? So you've seen one of the areas where generative AI has been used is for people who want to train their own GPT models, right? And they have GPT generate the text, and then they feed it, and what we're starting to see, the performance degrades. I mean, there are all this information that it may turn out that may not be a good approach of using that type of text. We're also going to go into an era, not just for us as we think about the downstream models, an era where it's very difficult to differentiate between what is generated using AI and what is, like maybe Akshay's original, writing or thought. And so there is a lot of society impacts even before we think, oh, I'm going to mitigate something like this. What I would like to caution is that it's not that easy as, okay, I didn't have enough Black patients. Now, Akshay has said I can generate more Black patients with the condition, voila, I'm done. I think that is a very sort of a concerning side, but as of today, and sort of like our joint research with Akshay, is that I see this as an opportunity to think about explanations from a non-technical point of view to the end user of the radiologist. If I'm saying, look, I think that this model is not working for people who are older, can I generate something like that and test, And so more than, hey, I don't have enough dark-colored skin for melanoma, I'm going to generate it. I think that's very short-sighted.
Awesome. Thank you very much, Judy, for the very insightful answer. And I apologize to the other participants who have asked questions in the chat box, and I don't unfortunately have time to go through them. I would like to bring the session to an end, but before that, again, a couple of housekeeping stuff. So first of all, for the continuing education, those of you who are SIIM members and attended today's talk, more than 45 minutes, you will receive your SIIM credits, and if any question popped up, please feel free to email info@siim.org for your answers. And after the session ends, you are going to receive, a window will pop up with a survey there. Please fill that out. It's going to be super useful, super helpful to us to understand your opinions about these webinars and make them better in future. And finally, please don't forget about our SIIM conference, which is upcoming, conference of machine intelligence and medical imaging. If you have not registered so far, please feel free to register before September 15th. With that, I would like to thank again from our speaker for their very insightful talks and all of you who attended our today's session, and hope you enjoyed the session as much as I did. Thank you very much and see you soon in our other webinars. Goodbye.